So in this video, we will take a look at charging an inductor in an RL circuit. By charging, I don't really mean charging like with a capacitor. In this case, we connect the inductor and resistor to a voltage source. In this case, via S1, right? If we close that, that will send a current across S2 if that's connected at A through the resistor, and the current will spiral around and go through this inductor, which, remember, acts like a solenoid and can generate and will generate a counter current to sort of inhibit or resist the increase in the magnetic flux. Okay, so what it effectively does is stifles the increase in the flow of current from the battery. Right, it's like a resistor, but it's not. Okay. So let's see. Let's see how an inductor, or how we can write it with Kirchhoff's law. Right. So epsilon, which is the voltage for the battery, that's equal to the voltages of all others. So just the R and L. So we have the resistor, the voltage drop, and the drop across the inductor, right? So I'm writing this as L, di dt. Notice this would be negative if I put this term on the same side as E, okay? In fact, let's do that. Let's put everything on one side because that's what we actually need to do. And then minus E, okay? Now that we have all terms on one side, we can see that this is a first order differential equation in I. Okay? And what we ultimately want to do is show how the current behaves in an RL circuit. Right? So number one, the resistor inhibits the flow of charge, but number two, the inductor does as well in a slightly different way. Okay? So you can brute force this if you want to, right? Utilize your math classes. You can also look it up in the book what the answer is. I'm going to write it down. The solution to this first order differential equation is, well, I as a function of time is some I maximum value times 1 minus e to the negative t over the time constant tau. Okay? That's the answer. Right? That's the solution, rather. So let's see the various cases as far as time goes, what happens to the current. So at time equal 0, what's the current? Well, if we plug in 0 for t, that's 1 minus e to the 0, which is 1. 1 minus 1 is 0. So there's no current flowing at the very instant of connection. Right? That should kind of make sense. If we wait an infinite amount of time, right? Switch S1 is closed. We wait an infinite amount of time for the current to run through the inductor and inhibit charge and counter current and all that stuff. If we plug in infinity, that's 1 minus 1 over e to the infinity, which is, well, 1 minus 0. And that will give us the maximum current, which, by the way, is just epsilon over r. Okay, that's the same thing, because we can treat this as, or with Ohm's law. Okay, so if we were to graph this, let's see what happens. Oops, I need more room than that. If we were to graph this current as a function of time, starting at 0 is 0. At infinity, it's some maximum current. So I max. It's an exponential, so it has to look something like this. Right? It asymptotically approaches the maximum value. And this tau, the time constant, you may remember that from RC circuits. Well, we don't have capacitors in here, we just have R and L. it's after the same percentage, or rather one time constant is the same percentage of the maximum. In other words, after one time constant has elapsed, the current in the circuit is 63% of the maximum. And tau, by the way, is L over R. After two time constants, so over there, the amount of current in the circuit is, I don't have room to write it, is 83% of the maximum current value, right? So it works the same way as it did for RC circuits, but in this case, tau is just equal to L over R. And so yeah, this is an RL circuit. We're charging up an inductor effectively for an RL circuit. That's basically it. In the next video, we'll take a look at after an infinite time has elapsed, we disconnect the battery and see what happens to the circuit, right? It's slightly different, still doable.